Perfect. Then let's get
Uh,
started. What can I do
yeah,
for you?
we can do. Let me look at the notes. I was actually we can go over the quantified statements. It's called quantified statements.
All right.
Some older stuff.
So, I like Tarski's World, and I like to play Tarski's World games. So let's see if I can bring up a Tarski World file. I'm going to share my screen. Let me grab. I think that was probably test one.
Yeah, that's this one.
All right, so here's one Tarski diagram. I think I have some other Tarski diagrams. Okay, there's a Tarski diagram.
Yeah,
So we can, we can play with any Tarski diagram. I don't know if you can take a screenshot of this thing.
yep. I took a screenshot already.
All right, you got a screenshot of it?
Yep, I got it on my phone, just sitting right here.
All right, perfect. So let's play some games with that Tarski's World.
Mm,
And
mm-hmm.
then I'll be able to post that file with the office hour notes.
Okay.
All right. So um, the kinds of questions that we get would be like this. One, give the negation. So we can practice with negating quantified statements. And then two, the instructions are always um, give the truth value of the original statement. And whether or not we use the original or we, decide we're going to look at the negation and figure out its truth value, and then the original will have the opposite truth value, that's entirely up to us. And of course, we have to justify. Okay. So let's just go ahead and so this is Tarski World B PDF that we're using. I'm just putting that there so I remember which one to post. All right, so here's one. There exists an X such that black X and above X comma I, where I is that particular object that has the name I. So does there exist an, so let's write the negation first.
There is this. Oh, the negation would be
For all,
for all black X.
for all X,
Well, excuse me, for all X. Yeah, for all X. But then we go negation of and statement or statement.
right.
So we'd go also, actually, no, we can't. So it'd be black X
Well,
or,
good. I'm glad we're doing this. If we negate P and Q, okay, let's just recall when we negate an and statement, it is true. The negation will be an or statement, but we have to negate both components.
so it'd be not black. It would be not
Yeah,
black X.
yeah.
Okay, cool.
So that for all X,
Not
X is not black, or, and do you remember how
or
to negate above?
is not above.
Yeah, we don't say below. We say,
Below,
yeah,
not above.
not above XI. So
X,
For all x, x is not black or x is not above object I. So I can share my screen again and we can look at this together to figure out whether or not it's true. I'm going to zoom in. I don't know how to zoom in here. Oh, here
I
we
can see.
go. All right. So the original statement says there exists an X such that X is black and X is above object I. Is that true or false?
When we say X, we're not talking literally about the letter X. We're talking about X as in any one of these variables that we have
Yeah, yeah. X is
at
a,
our disposal.
yeah, right. X is the variable, and X can take on any of the values A, B, C, D, E up to J.
I got you. All right, boom. So then that means that the negation is false.
Okay, so that means the original is true, and it's really easy just to um, justify why the original is true because the original is an existence statement, and existence statements are generally fairly easy to justify. You
Hmm.
just have to give an X that exists and explain, that it's black and that it's above I. So what X would you like to choose?
We can choose E.
Yeah, in fact, that's the only X
That's the
that
only
does the
X.
job.
Yep.
Right. So for this one, uh, take X equals E, and E is supposed to be bold, but that's good enough. Notice object E. We'll say enough about it to realize, for the reader to realize we're really looking at it, is a black triangle. So it is black. It is black. And E is above object I. Good. Do another one. All right. All right. Let's say this. Okay. For all X, left of X, D, or square X. Uh-huh. So it says for all X, X is to the left of D, or X is a square.
Says for
Mhm.
all X, X is left of D or a square. Okay, yeah, I got it.
Okay.
So wait, I have a question.
Uh-huh.
Right? Is it going to be mandatory to always write the negation?
Yeah,
Okay, that's good to
because
know.
a lot of times the negation really gives us an insight into what's going on, because sometimes it's not necessarily easy to see what's going on with the original. It can be easier to figure out what's going on with the negation. And when I say figuring out what's going on, I mean determine the truth value of the negation. And then we know the original has the opposite truth value of the negation. That by definition, they have opposite truth values. So that's why I always like you to take a look at the negation first. So let's write the negation.
The negation would be there exists X where X is not left of D
Mm-hmm.
and not a square. And then I can pull it up and actually go check to see.
So, so does there exist an X that's not to the left?
of, of D and is not a square. That's not to the left of D and not a square. Yes. And you could there's B, there's I, there's
Uh-huh.
G.
There's a bunch
So
of them, right?
and so yeah, the negation is in fact true. So we just got to go ahead and talk about it.
Right. So which object are you going to grab for the
I'm gonna
X?
grab B. I think B might be. I mean, they're all easy, but B. You could say B.
B works great. All right. So uh, here we want to go ahead and say the original is false because the negation is true. And now we're going to justify that the negation is true. Okay. And you wanted to let X equal
B
B.
let X equal B.
And now we have to explain why that X, which obviously exists, it's B. We have to talk about why it's not to the left of D and that it's not a square. So what do you want to say about that?
You'd say notice object B. Notice object B is is not to the left.
And in fact, it's to the right of,
To
right?
the right. Yes, to the right.
So that even shows a little more understanding, is to the right of object D
Of
and it,
object D, and it's actually a circle or not a
oh,
square.
so it's not a square B, you know? It's to the right, so that means it's certainly not to the left of, and it's a circle. That's fine. Good. Now let's get into multiply quantified statements where we have, either there exists, or for all, for all. Hi, Maxine Joy. We are looking at Tarski's world. So let's take a look at our Tarski world again. And now I'm gonna make up a statement that's got a for all there exists. All right, here we go. For all X, there exists a Y such that same color XY and same shape XY and X is not the same object as Y. That's what X is not equal to Y means. So for all X, there exists a Y such that X and Y are the same color and the same shape, and they're actually different
And
objects.
they're distinct.
hmm And so let's just recall a few things. Recall, for all X, there exists a Y such that P of XY means for each X, we can find a corresponding object Y so that the predicate P of XY holds true. So for each X, we have to find a Y that exists. So okay. So for every single X, we have to hunt for a Y that exists. Okay, so here we go. Let's take a look. So one by one, we're going to look at each object X and we're going to see if we can find an object Y that is the same shape and the same color and is actually a different object than X.
Say that one more time.
All right. So for each X, we have to find a Y that exists,
Mm-hmm.
that sort of like partners up with that X. So each X could have its own private Y. Okay.
Yeah.
Some X's might share the same Y, But the point is, for every X, we got to be able to find a Y.
And a Y that satisfies all the conditions that are in that.
And the conditions are they got to be the same shape.
Same color, same shape, same color, and they have to be distinct.
That's right. So we got to go through each X. If it's true,
So
we'll be able to go through every single X from X equals A all the way to X equals J, and we'll be able to find the Y that exists. All right, so might as well start with A.
A, nope.
Yeah,
Same color. G is the same color, but it's not the same shape. I mean, excuse me, this is the same shape, but it's not the same color.
that's right. There are no other white triangles besides object A.
Yeah,
So right there, we know that the original is going to fail, and that means the negation is going to be true. Let's go ahead and
true.
write the negation. All right. So the
There,
negation says what?
there exists X for every Y.
Such that
Wait,
for every Y,
excuse me, for every Y. Not X and Y aren't the same color,
so not same color, X, Y,
or
or,
not same shape.
uh-huh,
Not same shape. X and Y, and or no, excuse me, or X equals Y.
that's right.
So look, if we go and look back at it, my photos at. If we go and look back at it, I'll let you. But yeah, we look. If we go ahead and look back at it, then we just need to find X and Y that aren't the same color or aren't the same shape, and they're
It's not that we just find an X and a Y. We find an X that no matter what Y we look at, this predicate of the negation holds.
oh, so yeah, for every Y, excuse me, it's not
That's
just one of
right.
them.
But it's
So for
true that when X is A, then for every single Y, either that Y isn't white or it's not a triangle or Y is actually A. So you don't always have to explain it exactly, in a way that is too sort of formulaic. Your intuition is, hey, you know, triangle A is the only white triangle, you know, so there is no other white triangle. You can just say that. See what I mean? Where we
yeah,
don't, by saying it's white, we're saying every other white object is not a triangle, and every other triangle isn't white, except for X equals A, except for Y equals A itself. You see what I mean?
yeah,
So understanding what's really being said by the statement can help us create a natural justification for why the original is what? What's the truth value of the original? What did we decide?
false.
Yeah, the original is false because when x equals a, there is no other object y. When I say no other, that I'm dealing with the x can't be equal to y. That is a white triangle, and that deals with same color and same shape. See what I mean? Sort of in a more natural way,
Yep,
but still addressing all parts of this predicate.
yep, I hear it.
Okay. Now that was a for all there exists. The other way would be, the other kind of multiply quantified statement, with two quantifiers would be that has one of each, one quantifier of each kind of flavor here would be if the there exists comes first. So let's take a look at one of those because it gives us a chance to review the fundamental difference between a for all there exists or for each there exists, which is what we just dealt with, and the other kind of predicate statement, which is there exists an object that works for all. So now let's just continue. It's Tarski world B PDF right, D. There exists an X such that for every Y, okay, now I want to go back and look at our picture so I can create a nice statement. There exists an X such that for every Y below XY or same color XY. Below XY or same color XY. So let's think about what this statement is really saying, okay? First of all, it said there exists for all. So recall, if we have a there exists an X such that for all Y, something is true, some predicate P of XY holds, it means we can find one object, X, that works for every Y to make P of XY a true statement. So we have to find a single X that winds up working for every single Y. See how different that is than
Hmm.
when the there for all there exists, because for all there exists means, for each X, we can find a Y that might only be working for that X. But here we've got to find a single object X that works for every Y. Let's just go ahead and write the negation while we're sitting here looking at it, and then we'll go back and look at the picture and try to figure out what's going on.
And negation would be for all x there is just a y, not below x, y, and not the same color, not same color, x, y.
So that says that for each X, there's some Y that either, oh no, that is not
That
below
is,
Y
and
and
not the same color.
not the same color as Y. All right. But let's just think about this original statement. It says there exists a single X that no matter what Y we look at, including X equals Y, either, remember what below XY means. It means X is below Y.
Hmm.
The first variable comes out front, right?
Yeah, so, yep.
Either X is below Y or X and Y
X and
are
y the same
the
color.
same color. So let's see if we can find a single X that exists that's going to be below every Y or the same color as maybe some that it's not below.
To be, you use j.
That's right. J is below every Y except itself.
Yeah.
But when Y is J, then X is the same color as Y because we're picking X to equal J as
Hmm.
well.
So it's like we could pick either one, but yeah, either the same color as itself or it's either
Well,
below.
say, yeah. Well, no. J is not below J.
Oh
See
yeah, you're right. You're right.
that's
Yeah, you
why I
can't
had
choose either one. It has to be
yeah, that's kind of the point there.
that's
Because
of the
once we
or.
pick the
Yeah.
one that's on the bottom, it can't be below itself. So in some sense, below XY means X is sort of at the bottom. It's below everything else,
Yeah,
but it
it's
can't be below itself, but it can be the same color
the
as
color
itself.
as himself. Yeah.
So the original is what?
But the original is true.
Mm-hmm.
The original statement is true. Notice let let x equal J. Or no, this one, X equals J. What else do I say? When notice
Well,
when X equals J, X is not below or X
we're trying to prove the original. Remember, we're proving the original.
original. Yeah, so when yeah, you say X doesn't well J. I don't know how to position. I know how to say it in my head. You can say that J is not below every X, but it is the same color as sorry, X is not below every Y. So J is not below every Y, but because of the or, it is the same color as um it does exist. I don't know how to explain it. Can you
Want some help?
finish what's going on in my head
Okay.
for me,
J
please.
is below every object Y except Y equals J itself, right? Because J is in the bottom row by itself,
Hmm.
is in the bottom row itself. When Y equals J, then same color, J, J is true. So X equals J works for all Y, one way or another, either by being below or by being the same color.
When Y equals J. Yep. So yep, when Y equals J, then same color JJ is true. Yep. Because for
See?
every yep.
Right. So in some sense, we're splitting the objects Y up into two groups. The Y's that aren't equal to J, and then the Y that is equal to J. You know, either Y equals J or Y is not equal to J, right? And if Y is
Yeah.
equal to J, then same color, JY holds. If Y is different from J, then below JY holds. That's basically what we're doing. We're breaking it into these two groups of Y objects. Either Y is J or it's not.
It's
But
not.
but the predicate holds in both of these two cases, and these are the only two cases, because either Y is equal to J or Y is not equal to J. And no matter which kind of Y we're looking at, we will have covered all possible values for Y between these two cases. Do you agree? It's really kind of an argument by cases.
Yeah, I
Or
see
you
it.
could make this one case one and this one case two. It doesn't matter. I mean, I think when I wrote it, I kind of made Y not equal to J the case one. But the point is, we've covered every possible Y with this single X that you chose so wisely. You chose that X equals J. All right. Now, of course, we could, any questions on that? Are you good with that?
I'm good.
So we could have, other kinds of statements like this. For all x, let me take a look at this picture. Gray x implies above xj, for example. Gray x implies above xj. All right, now let's write the negation. This is good practice for negating an if
Um,
P then Q. How
well,
do we
this is
negate if P then Q?
it's an and. It becomes an and.
Tell me what the components are on either side of the and. You're right, it is an and.
It's gonna be if we call. Wait, so this is if this is a not P, then not Q.
No, 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 no. The negation of an if-then,
Oh, it's an and statement, so it would be
yeah, it can't be an if-then.
yeah, but I say it's an and statement, so it would be if not P then Q.
There's no if.
Oh, excuse me, not P and Q.
Okay, so you got it reversed. This is a way to try to remember it. P happened, the hypothesis happened, and the
A
conclusion
is
failed to
failed.
follow. Okay, so try to remember that's our
That's it. That's the rule when it comes to
that's the
negating.
rule for negating
Yeah, you're right. You're right.
an
I got
if
it.
then. And remember, every if then statement is actually universally quantified. And every universally quantified statement can be expressed as an if then. We might have to finagle it, but we can always just take the elements that are in the subset of the domain that satisfy the predicate and just say if X is in that subset of the domain, then the predicate is satisfied. The point is this: if an if then statement is always universal, and we know that when we negate a universal, we have to get an existential statement.
Hmm.
There's no way we could negate an if then and get an if then as
Yeah,
the negation, because then we'd be negating a universal and getting a
a
universal.
universal.
And we
That's not
can't
possible.
do, and that's how you can remember that the negation of an if then is never another if then.
If then, yeah.
All right, so what is the negation of this statement for all x? If x is gray, then x is above object j. That's what it says.
The negation is there exists X or gray X and not above not
Yep,
above XJ.
yep.
Yep.
Okay, great. That's exactly right. Now let's just look at this original statement and let's just see if we can understand what it says. It says that no matter what x we're looking at, if that x is gray, that object x is going to be above j. Okay? So let's look at our picture and let's look at our Tarski world. If x is gray, is it true that x is above object j?
Yes.
Yes, because what are the gray objects?
They're all above J.
Yeah, and we're
And
going to
J
name
is
them.
like that yeah, you can say like notice uh and then grab, or you could say I have a question. How would you position that if you're writing it down and you wanted to talk about
I
every
only
single
want to talk
X,
about the gray ones.
the gray ones? So
I
you
would
would
just list them. I'd say D,
list
F,
them.
G, and I.
Okay, yeah. All
See what
right,
I
cool.
mean? There are only four of them.
There's only four of them, so that's fine.
The only gray objects are D, F, G, and I. All of these are above object J, as J is all alone in the bottom row. Like we've already kind of talked about that. And here it just is another way to use that fact. Okay.
Hmm.
All right, let's do one more here. For all x, I want to do another if then because I think we need the practice. Triangle x implies right of x, g. Going to make it complicated. Triangle x implies x is to the right of object g.
The negation would be triangle x and not right of
Yeah, and what's your quantifier there?
existential.
Hey, Maxine Joy. There exists an X
Hi,
such that,
Dr. Good.
hey, thank you for giving me an email when I wasn't feeling good on Wednesday. That was sweet. And not right
No
of
problem.
XG. All right, do we all agree that's the correct negation?
Yep.
Yes.
All right, now we're going to just try to hold in our minds what the original statement is actually saying. Does somebody want to try to put in their own words what this original statement is saying?
For every x
Um,
that's a triangle, it's implied
that it's on the
that
right.
it's on the right of G.
Okay. Maxine Joy, do you want to rephrase that in your own words and give it a shot?
I was pretty much gonna say the same thing.
I have a question.
Yeah.
Instead of saying it's implied, you could say every triangle that's x is to the right of G.
You could just
The
say
original
every
statement.
triangle is to the right of object G. Yes, you could, because
Yeah.
this
Okay.
could
Okay.
just be written as a universal statement. Each triangle is to the right of object G. Or you could say if
Mm-hmm.
X is a triangle, then
It's
X
to the
is
right.
to the right of G. Or
Yeah.
X being a triangle implies X is to the right of G. Or you could read the whole thing for all X. If X is a triangle, then X will be to
It's
the right
right
of G.
of G.
All right, so let's
Okay.
take a look. And let's see if we think it's true that if X is a triangle, then X is definitely to the right of G.
If x is a triangle, then it's to the right of G. That statement is false.
Oh,
Yeah, I
Maxine
think
Joy, do
it's
you
false.
concur? Okay, so it's
Yeah, I
false.
do.
Tell me a counterexample. Why is it not true that every triangle is to the right of G?
Um,
Mm,
let notice, or you can say let, or like notice the negation. There's an existential. So it says the negation says, uh, a triangle at like let x be
There
a triangle.
exists an X.
There exists
mhm.
an x that's a triangle and not to the right of
It's
G,
not.
in which A fills that A
It sure does.
represents that existential statement. So
It
we would say
represents the X. That's right. X equals A
Mhm.
satisfies the negation.
satisfies the
There's
negation.
another X that would satisfy the negation. Do you know which
That's
one?
itself. The
Right,
original doesn't say that they have to be distinct. So you could just grab the original and say, hey, look, it's a
that's
triangle
right.
and it's
Nobody
not to the right
said
of.
and X is not equal to G. X could be G and X equals G
Yeah.
works too. Very nice. Good job. So see, that's a smart use of the negation. You looked at the negation and you were checking the negation to make sure your X satisfied. Oh, my X is definitely a triangle, and the X I'm choosing is not to the right of G. That's really smart use of the negation. And that's what we're shooting for. We're shooting for an intelligent use of all the information that's in front of us. So write it up. Remember to answer the question, is the original true or false?
It is false
Yeah,
because the
say that first. Mm-hmm.
negation holds true. True, you could say notice let x equal. Actually, we could actually I'll use itself.
I like that. That's very
So
brave
let
and
x equal
very correct.
so let x equal g.
I like that you're using notice.
X is a triangle, or you could say G is a triangle.
Uh-huh.
G is a triangle, and it is not to the right of itself.
Nice. So notice X equals G is a triangle.
Not to the right of itself, and then after that you could say notice um in the or you can say notice in the original statement um there's nothing saying that X has to be disjoint.
Distinct,
Oh,
distinct
distinct, excuse me. Thank you.
from G. There was no requirement that we pick an X different from G. Because if there had been, this would have said right of XG and X not equal to G. But even if we had said X can't be equal to G, then what X could we have used?
Just A, we can just use A, in
Hmm
which the negation still is true.
That's right. We could have used X equals A, even if the requirement was that our choice of X is different from G. And that could have been, that requirement that X not equal G could have been in the hypothesis or the conclusion. It wouldn't, either way, we could still use A. Nice. I'm really glad that you're asking really smart questions, Isaiah. I think you'd make a good teacher. I think you are seeing exactly the questions that I'm going to want to be asking. So this was a really good question. So Sean, I see you just joined us. We've been sharing the screen with this particular Tarski World B, but I will post it with the office hour notes so that you can go back and see that as well as in the video. Okay.
Okay.
I'm glad that you made it. Okay, Maxine Joy, it's great. So Maxine Joy, it's your turn. Do you have a particular question you would like to look at? Or some topic that you would like to explore tonight?
Not at the moment, Dr. Good.
That's fine. That's fine. People just come and hang out. Sean, how about you? Did you come in with a particular topic or question on anything, quiz, test, worksheet that you wanted to look at tonight?
Um, I wanted to look at, hold on, give me a moment.
That's fine. I'm not meaning to put you on the spot.
Okay.
Mm, Isaiah, did you have another question or a topic that you also wanted to explore tonight?
Sorry, I went to go get some water. We can go over proof. Uh, we said proof by devise. We did proof by devise. Um,
How about a
I would
proof
say,
by cases?
yeah, we can do a proof by cases. Yeah, yeah, yeah. That's good. That's good.
Because we haven't looked at proof by cases yet. So I'll put a couple of examples here and then we can look at them both. If n is an integer, then n squared plus 3n. Huh. Dr. Good is having a,
Ready for it?
yeah, I didn't want to say it, but you said it. Odd minus odd is even, even plus even is even. I want this to always be odd. Well, good Lord, hang on. I gotta look at something. Now I'm worried. It's like my brain stopped working for a minute.
My door.
Oh, it's okay. I just got worried for a minute.
Squared plus 3n.
Plus, minus 5 is always odd. And here's another one. If n is in z, then 3 divides n times n plus 1 times n plus 2. Okay. All right. So if you remember proof by cases, our steps were to,
First when we find find D.
yeah, discover the divisor D. And to do that, we look at the conclusion. And then that's step 1. And then step 2 is apply the QR theorem using the D from step 1 and apply this to the integer in the hypothesis. So we're going to break it up into cases based on the divisor D that we have discovered by looking at the conclusion. But we apply that divisor to the object in the hypothesis, and that's always going to be an integer for us, okay? And there are, other cases. For example, we proved by cases either the y that we picked was equal to j or the y we picked is not equal to j. And we also have cases when we do set theory proofs involving union. If X is in A union B, then X is in A or X is in B. And then we have two cases. But for these proofs, based on the QR theorem, it's always going to be an integer that we're applying the QR theorem to get our cases. We get D cases. So if, D is 5, we would get 5 cases. If D is 2, we get 2 cases, et cetera, et cetera. All right, so let's look at example 2. What is the divisor in play when we look at the statement of example 2?
What is the divisor
Yeah,
that
what are we
in
trying to
example
prove?
2?
Yeah, why do
We're
you
trying
say
to
that?
prove um we're trying to prove that 3 divides n um n plus 1 times n plus 2.
Oh, you're looking at example 3. I'm
Oh,
still,
excuse me. I'm tweaking. My fault.
you're fine, you're right.
Example 2. Excuse me.
Let's look at example 2 first, and then we
Yeah, of
will do
course.
example 3.
Of course. Um we're trying to prove that n squared plus 3n is minus 5 is always going to be odd. So we're going to have two cases, and it's
Yeah,
going to
because
be
we're dividing by 2 if we're trying to show something is always
so.
even or odd.
So we'd have two cases, 2k plus 2k and 2k plus 1.
Good. And then in example 3, what is D going to be?
I would say two cases again. Oh, excuse me, three.
We're trying
Because
to show 3 straight up divides this. So that means that when we look at n times n plus 1 times n plus 2 and divide it by 3, we get a remainder of 0.
of 0. So we'd be checking three cases,
Uh-huh.
0,
All right.
1, 2.
Mm-hmm. That n either yields a remainder of 0, 1, or 2 when we divide it by 3.
Add
All right,
3.
so let's
Mhm.
let's look at example 2. Our proof, we're going to let n be an integer, and using D equals 2, the QR theorem says, remember we have to use the QR theorem, and we have to use the QR theorem to set up the cases. It says either n is equal to 2 I'll say Q, or N is equal to 2Q plus 1, right? Because it's 2 times the quotient. That's why I'm using Q here, but you can use K. It doesn't matter. But the point is, we have two cases. Either N is going to be even, in which case it gives a remainder of 0 when we divide it by 2, or N could be odd. In both of those cases, we wish to show that N squared plus 3N minus 5 looks odd, so we want to show it equals 2K plus 1, right? Where K is an integer. We want to show that in both cases. Does that make sense?
Yep.
So we've set up our two cases using D equals 2, applied to the integer in the hypothesis, and now here we go, case 1.
We just attack both cases. So you do case
Yeah,
one.
attack the cases. Suppose N equals 2 times Q, where Q is in Z. And then what do we look at? What do we examine?
I wish.
Yeah, let's look at our wish. Look at our wish, our dreamy wish here. And it's a two-part definition. To show it's odd, we have to show it, meaning N squared plus 3N minus 5,
Minus 5.
looks like 2K plus 1,
2K
and
plus
then we'll
1.
have to talk about why K is an integer using
So,
closure.
mhm.
So here we go. N
We can do
squared plus 3N minus
yeah,
5. What does
so
it look
right into
like?
substitution.
Mm-hmm.
Minus 5 equals um 2Q 2Q
Quantity squared.
squared
Yeah,
to
the whole
quantity squared, but
thing.
you want to make sure that it's in parentheses, yep.
Yeah.
And then 3 2Q, and then you can just go minus 5,
Yep. I'm liking it.
and then just go ahead and really get into that.
So what do we got?
So we got 2Q. Technically, it's 2 squared and Q squared, right? So
Yep.
it'd be
So
4Q squared.
good.
4Q squared plus 6Q minus 5. And then you would break down 5 into, you could say it's 4. You could say it's 4 plus 1. So you could say minus 4 plus 1.
That's not minus 4 plus 1.
We can't break down
We
5
can
into
break
4
it
and 1.
down, but we can't break. It would be negative 4 minus 1, but we don't want a minus 1 hanging off. We want a plus 1.
You want a
So
plus 1?
we want a plus 1, right? Because we're going to want a
Yeah, of
plus
course.
1. So what is this number going to have to be? We're applying the QR theorem to N equals negative 5 right now. We're dividing negative 5 by 2. So it's really 2 times negative 3. Remember, we have
So,
to overshoot to the left and come back with the positive 1. So this is really a negative.
negative, negative 6.
Okay, remember
Giant.
that? Remember that?
Yeah, you're right, because it's not a plus right there, so I
Oh
can't
yeah,
just
it's a
blanket.
minus 6.
I
Yeah,
can't just
yeah,
blanketly
right.
just change it. I have to account for
Right.
the negative
Right.
of
We
the
know we
minus
need a
6.
plus 1, so we look and see what the other summand is. It's negative 6. Now what do we do?
So now we could factor 4Q
Yep, because we
squared
want to
plus
get a 2.
6Q minus 6. We could factor 2 out of that, which gives us 2Q squared plus 3Q minus 3 plus 1 on the end, in which um
And
we could
this
say
and
that
this is our K,
is that's
right?
K, right? So we have 2K plus 1.
Yeah, but we got to talk about why this really is an integer.
Yeah,
See,
we have to use
used the
our
fact that
monies. You have to
Q
use
is,
our monies.
yeah, we haven't used the fact that Q is in Z yet. We used that N equals 2Q. Yeah, we burned that, but we hadn't used this money yet.
You could
So we
say
need to use that.
K equals K equals what would
K
you
is an,
say?
since K is an element of Z.
Since K is not another C.
Oh, is it K or is it Q?
No, Q. Wait.
Yeah, it's
I mean
Q.
it's Q, but you can
It,
like
it
pick
depends
where.
upon, right, depends upon what
Yeah,
variables you use. I'm using Q
yeah.
though, so I better say Q.
Q. Yeah, since Q is an element of Z, right? You can say
Uh-huh.
K. K equals squared plus 3q minus 3 is an element of z because I have a question right here. Now, I don't know, right? Probably we're definitely doing sums and differences, right? Because we have subtraction and addition, right? Because of that 2q squared, we also put products.
That's right. So because products, sums, and
Sums and
differences.
differences of
Good.
integers and differences of integers are integers.
Perfect. So now we've got part 2 of the definition of odd satisfied for n squared plus 3n minus 5. So we could just say, so n squared plus 3n minus 5 equals 2k plus 1, where k is in z, which makes it odd by definition of odd.
By definition of odd.
And that's case 1. I'm going to get some water while you start case 2.
Mm-hmm. Yeah.
All right. I got that far. Did you get that far?
Almost not completely not yet.
It's okay. But I'm stuck because I need a +1 and I don't have a +1. So you're going to help me with that.
So you said n squared. You said 4q squared plus 4q plus 1, of course, plus 6q plus 3 minus 5, which ends up being 4q squared plus 10 because you sure about that in there. So I have 4q, 10q, basically.
So what is how can we rewrite -1 so we see a +1 as a summand?
You multiply it by itself.
And just solve for x. Just call this thing x and solve for x.
So for x, -1 equals x. I'm a little confused, but it's supposed to be super simple.
Solve for x. How do we get the x to stand alone? Subtract 1 from both sides.
Q0. or you get -2 on
I
that side,
do.
and then you get
I mean, for me, -2 plus one is.
-2 plus one is what
I don't know what world you're
is
living in.
we're living in. What? Zero?
What?
Nah, I feel it. Uh,
You live in the world where -1 is equal to +1.
living on Mars.
That's awesome. Does that mean all of my negatives in my bank account are going to be positive now?
That's what it means for me.
I'm loving it. I wish. If you hear me in here, I've I boiled some water in my tea kettle. I'm sterilizing my stainless steel water cup. Every now and then, every couple of days, I sterilize it with boiling water. Otherwise, it gets germy. Okay, so what do we got? So this is 4q squared plus 10q minus 2 plus 1, right?
Yeah.
All right, now what are we going to do? See, you see why we're doing that.
Yeah, we did that so that we could put 2 into like our factorization.
Yeah, because
So
we need a
now
plus 1 hanging off, right? For
we
this to
need a
turn out
plus
to be
1 hanging
odd.
off.
Yeah. Definition of
So we
odd does not allow a -1, does it?
no, it does not.
No, it
It
does
must be
not.
+1. So then we get +1.
So
So we
tell me
get
about my K here. We're building K now.
plus
Help me
2.
factor the 2 out. What do we got left in here?
We got 2q squared. We got 5q. Then we got a 1. Or we have a -1.
We do.
So
So we got
it's going to
half.
be very similar to what we just did.
Right.
Right? That's K. So then we got to speak about it, right? Since Q is in G, uh, notice K, notice K equals 2Q squared plus 5Q minus 1 is an integer
Same reasons, right?
because products, sums, and differences
Nice. You got this.
of integers are integers. So what was it? What was the original statement? It was what? N squared plus 3n minus 5 equals is odd, or you could put it equal to 2k plus 1 is odd by the definition of odd.
Full credit.
That's case 2. That's a full credit case 2.
That's a full credit proof right there.
On the test, do you want us to say something about both cases holding true at the very end, or just
It's
saying case
okay.
1 and case 2 is fine?
You know
Okay.
what? If you actually prove both cases, then I know you understand enough to realize you need it to be true in both cases. So yeah, I
First,
mean, you can say we have proven it in both cases, but on the final you might be kind of pinched for time. So
yeah.
just prove the two cases completely. Make sure you talk about why K is an integer and you'll get full credit. You'll be fine.
Oh, all right, cool.
I'm going to write down
Uh,
example 3 right here so we can see it. It says if n is an integer, then 3 divides the product of 3 consecutive integers. We did this one. This was a special homework problem, I think. Remember way back
Probably
when
like
you look at
what
this was
2 months ago.
I know, but think about, it was hard then, but now it's just like, okay, it's coming
Now
back.
it's just refresh, right? Just a
Hmm.
refresh, right?
And we already
It's gonna
looked at
be
that and we realized, hey,
D equals
the
3 base
conclusion
2.
is talking about dividing by 3. So D is going to be 3 because we need to get some threes into the mix. You see what I mean?
Mm-hmm.
Like we're
Yeah,
going to try to pull a 3 out and get a remainder of 0. We got to introduce some threes. How do we get some threes into the picture? We're going to split N up into 3
to
cases
3
based
different
on
cases of 0,
D
1, and
equals
2.
3. Right, right.
Um, D equals 3 three cases. Those cases are gonna be we're dividing. By the QR theorem.
Yeah, by the
Dividing.
QR theorem. Yep, that's the way we introduce the cases, by the QR theorem with D equals 3. We've got that N equals 3Q or N equals 3Q plus 1. I mean, the bottom line is we know we can divide N by 3 and we're guaranteed to either get a remainder of 0 or 1 or 2.
Okay. Or
So this one, yeah, this one, it's 3 cases. It's going to take a bit of doing, but we can make our life a lot easier by factoring rather than distributing. You'll see what I mean when we get to it. You'll probably even remember.
we do case one.
What
Type
should we
case one.
suppose? What should we suppose for?
Suppose n equals 3q.
Okay.
3q. Um, by
And
the
you know what?
definition of
Because I don't want to
divides.
say all this stuff a million times, I might just say that all at the end. We'll see. We'll see if we can figure out a smart way to say all the stuff about the integer part.
About the integers. Okay. So we're supposing that n equals 3q, right? Where q is in z. But also, by the definition, we're not just dealing with odd and even, we're dealing with divides, right?
We're dealing with divides with a bigger divisor than 2. That's exactly right. We're dividing by 3.
So,
Remember, when we divide by 3, it splits the integers up into 3 subsets, and they're called 3z, 3z plus 1,
and
remember,
3z plus
or
2.
3z
Yeah,
plus 2, whether, based on whether the remainder is 0, remainder
1
is
or 2.
1. And this is congruence mod 3, dividing integers by 3 and looking at the remainders and grouping them by remainders. This is the congruence mod 3. A is congruent mod 3 to B if 3 divides A minus B, or if A mod 3 equals B mod 3. In other words, if A and B have the same remainder, when they're divided by 3, we say they're related to one another. They're congruent to one another, mod 3. And
Mm-hmm.
that congruence partitions the integers into these 3 subsets where integers are all grouped together in the same subset. It's called an equivalence class. It's an equivalence relation if the integers have the same remainder. So all of the 0 remainder integers live in 3z. All the remainder 1 integers live in 3z plus 1. Remember? And
Mm-hmm.
all the integers that yield a remainder of 2 when divided by 3 live together in 3z plus 2.
Interesting. So it would be
So we're talking about
like,
congruence mod 30 right here.
for example, like a real world example or like a real math example would be like that 3z plus 1, like 7 would live there,
Right.
16 would live there, so on and so forth. And same thing with 2.
Exactly. Yeah, yeah, yeah. I mean, if you look at the number line, then every third integer would be in the same equivalence class.
Yeah. Boom, 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 and then boom, 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 and then like anything divisible by 3
Right. So we could
is
put
just gonna live in
circles for the
at 3z.
zeros, right? So all those are in 3Z. But then we could put little squares, like you were saying, 4 and 7 and
Mm-hmm.
-2. You just got to jump by jumps of size 3. 1, 2, -5. Those are all in 3Z plus 1. And then you could use like, green triangles for 3Z plus 2, like 2 and 5 and, 8 and -1. And what would this one be right here?
Uh, negative,
-4, I think.
-4.
But remember, I mean, so and what we're saying is, hey, if you take the product of 3 consecutive integers, they're always going to be in the class of the circle. They're always going to be just multiples of 3 because 3 is going to divide that evenly with a remainder of
Mm-hmm.
0.
I
All right.
understand it.
All right, so what is the expression we have to check out? What do we wish to show?
We wish to show that 3 divides n plus 1 times n plus 2
Let's just break that down using the definition of divides.
of divides.
So what do we really wish to show? We wish
We
to
wish to
show that
show that n
n
plus 1 n plus 1 times n plus 2
is equal to 3 times k,
and d times k, where k
because
is a
that's what
d.
it means to say 3 divides. It means the remainder is actually 0, right?
Yup. Yup.
All right, so that tells us we got to look at, this is our wish, right? We got to look at n times n plus 1 times n plus 2. And we got to show, this is our wish, right?
Yeah, let me go ahead and put that in curly brackets just so that I know that's mine. Don't get that confused with
And
my
here's our proof
hypothesis.
money.
Plus 2 equals 3k. K is on z. All right, cool. So then now isn't this is where we attack the so actually this is where we attack the n plus 1, n plus 2.
Yeah, we're going to attack that.
So what that really looks like is going to be n plus 2 is going to be 3k.
I
Or
think
we
I'm
should actually 3q.
3Q, but if you use K here, that's fine. Just be consistent.
3q 3q plus 1 times 3q plus 2.
Now, look, don't multiply all this out. That's what I was saying.
Mm.
Don't distribute all this stuff and like get K three, 27K
And
cubed or
be,
whatever. No, don't do it.
yeah.
We have a 3 right here. We can
Mm-hmm.
pull that
Wait,
3
we could
out
just pull the 3 out of everything, right?
and just out of right this one factor, pull it out of the one factor, and then the other factors just stay the way that they are.
So you get what 3,
And this
and that
whole
and that
thing right here is
is
our
gonna be our
K.
is our k.
Yeah.
Wow,
And
I didn't
then
know that trick.
now talk about K. I'm not going to do it, okay?
But yeah, we
You
know how to
know,
do that.
yeah, we know how to do that. That's the easy
We've
part at this point,
established that
I think
skill.
it's just sums and products, right?
Mm-hmm.
All
Some
right,
more
let's
products.
attack case 2 then. And let's take a look at how it
So,
looks a little different than case 1.
alrighty. So, um, you wish to show in case 2. Case 2, of course, that 3 divides n plus 1, n plus 1, n plus 2, and n plus 1, not just n plus 1. What that also looks like is going to be n, n plus 1, n plus 2 equals 3k plus 1.
Oh, no, 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 no,
Oh,
no. No, it's the same wish. We want to get a remainder of 0. In every case, we want 3 actually divides this product. That
so we
means
want
even if the remainder for n is 0 or 1 or 2, we want the remainder when we divide this expression by 3 to be 0.
0.
And
So we're
I'm
always,
so glad we're talking about that because that is the most common error. Students think that just because we're in the case where n equals 3q plus 1, that our wish has changed. No, no, no. We still wish to show that 3 straight up divides n times n plus 1 times n plus 2, i.e., that n times n plus 1 times n plus 2 is equal to
is equal to
3k.
3k.
Yeah,
So
we
we would
want
just
that no
substitute
matter what.
using
Yeah, now we,
wrong, we're just
yeah,
substituting with
yeah,
3q plus 1.
yeah.
Yeah, that's the trick. You know how I didn't write my suppose first?
Or you were thinking it, but then you were applying it to your wish.
Yeah, I was applying it to my wish without actually paying attention to what I'm assuming and then what I'm
It's the
actually wishing.
same wish in every case. I'm so glad we're having this discussion because that is such an easy mistake to make in these proofs, where you get confused between the hypothesis of a case and the wish, which doesn't change. Now,
Mm-hmm.
sometimes the wish might be uh, a disjunctive statement. It might be an or statement where you want to get this or that, but it's still the same this or that, no matter what case you're in. I'll
So,
give you a do
and
later. I'll give you a do later. But anyway, let's go ahead now. All right, so we got to use
Um,
parentheses now because we're substituting in a, what do we call this
a
thing?
binomial.
Binomial for n.
So
So,
3q plus 1. Make sure that's in parentheses. Parentheses. 3q plus 1 plus 1. That's a good highlight. That's good. That's good to write.
and that way we're
3q
at least
plus 1
seeing.
plus 2.
So now let's take a look. I'm just going to simplify the factors. It's 3q plus 1 times 3q plus 2 times 3q plus 3. Do you agree?
I do agree.
I still don't want to multiply all that out. I'm lazy. I do not want to multiply all that out. I'm looking to pull a 3 out. Well,
Well,
we
tell me the
cannot,
trick.
yeah, you can't pull a 3 out of 3q plus 1 because the 1 doesn't have a 3 as a factor.
Yeah,
We cannot factor a 3 out of the factor 3q plus 2 because 2 doesn't have a 3
2
as a
doesn't have an
factor.
actor. Yeah.
But looky here. We got a 3 here and a 3 there. Isn't it true that we can factor a 3 out of here and have q plus 1 left over? Now we got 4 factors and one of them is a 3.
Yeah.
And then we just pull that 3 out front.
So once we pull that 3 out front, and it
Yeah, because these
passes.
are just multiplied together. You can slide them around any way you want.
Yeah, you're right. It's literally just manipulation.
It's just understanding what multiplication really is. Yeah. And this big ugly thing's going to be our K. And we're going to, talk about K, do later.
Yeah, this is ugly, but I mean, it saves time.
But yeah, otherwise you spend 20
I would
minutes
sit there.
multiplying all that out and it's not doing anything for you.
Yeah.
Because you're going to still wind up with products and sums at the end of the day. Just leave it as this product, with of products and sums.
Uh-huh. And then
What's
let's
case
then
three? Let's look at case three.
case three
What are we
is
going to
that we
suppose?
suppose n equals 3q plus 2, where
Hmm.
q is an element of z. Then we write our wish. When our wish doesn't change, it stays the same.
Right.
You should show technically 3 divides n plus 1, n plus 2 times n plus 2. What that already looks like is n plus 1 n plus 2 equals 3. Okay.
Right.
So then we put some bubbles. Actually, we don't even need bubbles. Actually, we put some bubbles, but we're about to attack it anyways. So um n plus n plus 1, and then n plus 2. That really looks like, actually, I'm gonna write it in a different spot on my notes.
You're running out of room.
No, I was writing onto the side when I need to go sequentially bottom to top. It's way easier to look at it that way. That's probably how a lot of like your readers gonna read it. So it'll be 3q plus 2, and then 3q plus 2 plus 1, and then 3q plus 2 plus 2. Can we simplify that? Then we just go to the middle so we can look at that middle one.
Yeah. You
We
see
just
it,
look at the
don't you?
middle one. Yeah. So when we take out that middle, and then uh, that's ended up being what, 3q, or excuse me, 3, and then you're only gonna
Yeah,
have
it's a 3
q
times
is
q
q, which is
plus
q plus
1.
1. So literally, you just take out this 3q plus 3, and then grab that 3, bring it over here, and then it's 3q plus 2, big parentheses, little parentheses, q plus 1, and then we have a 3q plus 4 on the outside, and that's our k. And then we say something smart about k.
Exactly. I like that. Say something smart about K.
That's
I
how
love it.
I got a really good grade for I think that I got a really good grade on test two, and that's kind of how I got my full credit for my questions. What do I say? Like say something smart, and then like it would just come.
Right. So good. I'm glad that the method worked for you because really, if we really do think about, we got to use what we got here, right? We got to use what our proof money is, and here's our wish, and just keep your definition straight. Then you're golden. Yeah. So
Doesn't
that's
change
nice. So three
based.
cases, and in every case we get that same resolution. And doesn't it make sense? Because think about it. If we're taking three consecutive integers, so we're taking like a triangle followed by a circle followed by a square, or it could be a circle followed by a square followed by a triangle, or it could be a square followed by a triangle followed by a circle. But the point is, if you take three in a row, one of those puppies is going to be a circle, and
Yeah,
it's got the three in it.
yeah. I was just thinking about it, and it was just, yeah, I was just thinking about it. I was just like, yeah,
One
that
of
makes
those
sense.
three factors is going to be in the set 3Z. And whether that factor is the first factor, that means we're looking at circle times square times triangle, right? Or if that factor of three, winds up being in the last factor, right? That means we're
Yeah,
looking at a square times a triangle times a circle, because, the three's in the last factor. Or if it's in the second factor, that means we're looking at a triangle times a circle times a square. If you take any three of these in a row and multiply them together, well, you got three of them. Every third one is
every
going to
third
be a
one,
multiple of
or one,
three, and it's
one of
going
them
to
is going to
have
be a multiple three, and you factor that, and you factor it out. You know,
exactly.
no matter
And it
where
would,
you're at.
right. If you wanted to, and so, that idea of consecutive integers, being divisible by a divisor d, well, we remember this, n times n plus 1 is always even. Well, we're playing the same game. These are two consecutive integers, right? Except d is 2, and we're just saying, okay, you know, even odd,
Yeah,
even
even
odd,
odd,
even
even odd.
odd,
Yeah,
even
yeah,
odd, even odd, even odd, right? Zero,
yeah.
2, 4, right? 1, 3, 5. If you take any two of them, either the first factor is going to be even, or if you take 3 with 4, then the second
The
factor
second one's
is,
gonna
but
be
one of
even.
these two is going to be even.
Yeah,
You can pull the two out.
I feel it. Nah, yeah.
And if it was n times n plus 1 times n plus
Uh,
2 times n plus
One plus
3,
three.
it
Your factor
is
is gonna be
divisible by what?
divisible by four. I mean that no matter where
Yeah,
you're at, you're gonna have to grab, and well, no matter where you're at, you're gonna grab a factor of four, and you're gonna
it's
get
going to
a
be one of them.
divisor of zero. Yep.
Exactly. Exactly.
Or not, but yeah, it's gonna divide by zero. Basically, you're not gonna get a remainder. So
When you divide it by 4, you'll get a remainder of 0.
of
That's what you're
zero, no
talking. That's
matter
what you
where you're
mean to
at.
say. Yeah.
Exactly.
All right. Well, we have been going for about
Almost an
85
hour.
minutes here. Oh, Jonathan has joined the party. Hi, Jonathan.
Howdy.
Good, good to have you in our hangout here. We are just wrapping up. Let's see what we did tonight. We looked at a Tarski World game, and I'll post
Fun.
the Tarski World with the notes. We went back and forth sharing the screen with the Tarski World, but I'll post it. Then after Tarski World, we've been playing proof by cases games.
Oh, nice.
Yeah, we did this classic that this trinomial is always odd. Then we did that the product of three consecutive integers is always divisible by 3. So we sort of reviewed the steps for setting up proof by cases. And then we went through example 2 thoroughly. And with example 3, we got a little lazy on it, but we killed it close enough. And we talked about some general concepts having to do with the way that dividing by 3 and looking at the remainders is a way to partition Z, and that is the congruence mod 3
Hmm.
equivalence relation. And the partition of Z has three partitioning sets. The three equivalence classes are 3Z plus 1, and 3Z plus 2. So that is what we have been doing. Did you have a particular question that you wanted to ask?
I'm glad to hear that y'all went over. Well, yeah. I'm glad to hear that y'all went over proof by cases. That's one of the things I wanted uh, to talk about. I
Great.
think some of the stuff I had jotted down that I wanted to go back over were like some of the recent stuff. So like equivalence relations, recurrence relations, RC stuff. I think that I'll be able to handle that pretty well. Um,
So let me just
Proofs by
point you.
contradiction and mod and div, I think probably are the things that I struggled with more than those things, though, if I had to be honest.
Okay, well, let me just show you what's available
Mhm.
in YouTube.
Oh, have you
Because
uploaded some more stuff?
we have had an office hour every night this week. So the 5th, so Friday was, so the 5th was Friday, the 7th was Sunday, Monday, Tuesday, Wednesday, today's Thursday. So, but the thing that I have done here is I have put the topics. So I don't want to start these videos, but you see how I've listed the topics that we covered in the description.
Oh, uh-huh, uh-huh.
So you will see that we did talk about proving a sequence satisfies a recurrence relation. We did do that on the 5th of December.
Oh, brilliant.
Uh-huh. And then I'm just trying to address the questions that you had said. Let's see, on the 7th, we did double subset inclusion
Mm-hmm.
and talked about, interval notation. That might not have been, what you needed. But then on the 8th, we did talk about things from questions having to do with mod D.
Mm-hmm.
Like you were saying in the elevator, poor div. Nobody cares about div. And it's
Uh-huh,
true, nobody cares about div, but the A mod D problems are a little tricky. So if you
uh-huh.
look at the video from the 8th, we did an extensive sort of deep dive into A mod D, and there were some do later problems there. And then oh yeah, and then on the 9th, we talked about binary relations and we talked about the fact that the empty set is actually a binary relation and it's symmetric and transitive by false hypothesis. That was sort of the gravy.
Yeah.
I mean,
Yeah, that's fun.
that's kind of fun, but we did do quite a bit with the binary relations, and we talked about proof by mathematical induction. And then we did a bunch of stuff last night, drawing the directed graph. I think I made a mistake in the lecture. I called it an arrow diagram, but then I corrected that in the class notes, or at least I said, please, it's a directed graph. But
Oh,
we,
uh-huh, uh-huh.
I was tired that day. But anyway, binary relation, and then we worked on some of the chapter 8 stuff. Then we looked at proving and giving a counterexample for primes and composites and proof by contradiction. This particular office hour, Isaiah was right on point. Like he was asking questions that they're going to be, they're going to look a lot like final exam questions. So I definitely recommend checking out 1210. And then tonight is the 11th. And so, dip into those as needed. We'll have one more office hour tomorrow night, folks. Um, is the 7 p.m. time a good time for people, or does it need to be a little later?
I think tomorrow a little later would be convenient for me, but I understand if, everybody else's
A
schedules are
So
little,
different.
actually, a little later kind of works for me too, because I
it
have
is
work from 10 to
Friday.
7. Yeah,
Okay, so tomorrow night, how about we do an 8 p.m. then?
that's good. 8 p.m. sounds good.
All right, and it's not like you don't have plenty of stuff to work on, folks. You've got lots of due laters, and you've got lots of office hours to watch. So you've got
Thank
plenty.
you so much for posting all of them. This is really great.
You're welcome.
So thank you for being accessible. A lot of classes you don't get the opportunity to have office hours every day for the final exam.
Yeah.
So thank you.
Right, but there are people who have asked for pop-up office hours, and I've always tried to give them. There have been lots of office hours, whether it's just been me and another student just chatting for an hour and a half because nobody came into office hours. The one thing I would just say, folks, is hold your professors to their office hours. And if a professor says, hey, all you got to do is ask, there aren't that many that'll say that, but if they do, ask from week one, from week two, and take advantage of it. It's private tutoring, it's coming from the horses or the old nag's mouth, right? So put that in your hatemyprofessor.com comments that, hey, at least, with Dr. Good, go to her office hours because she will have them and you will get your questions answered if you bother. It's sort of the 11th hour now, but I'm so glad that people are coming, and hopefully it's more of a refresher than a first time. But there certainly are little things that we can get wrong. And it's nice to get it sorted out once and for all. Anyway, folks.
Yes, that is true.
All right, so tomorrow night we'll do 8 p.m. office hour. Get your questions lined up, and let me get this stuff posted. And have a great night.
Have a good night.
Thank
All right,
you,
thank you,
Dr.
Chris. Have a good
Good.
night.
Thank you
Thanks,
so much.
Isaiah. Thanks,
Thanks
Sean.
again.
Thanks,
Of course,
Jonathan.
of
Good,
course,
always good to have you come on.
of course. Thank you so much.
Thank you,
Yep.
Dr. Good. Have
You're
a good
welcome,
night.
Exie and Joy.